I'll just upload once a month.
It's been 2 months, you lump of cement!
Freaking celery!
And also school started.
And raisins! Good day, my fellow scholars. 'Tis I, Davis, a ball of fluff, and this is Fluffball the Wizard. Okay, I realize it's been a minute. I'm just gonna skip to the content because nobody likes when YouTubers are like, I haven't uploaded forever, I'm so sorry, I've been busy. I'm doing it right now, aren't I? Gosh dang it. First of all, I want you to take a minute to appreciate the camera rig that I have. I have my main phone here as my primary camera. I've got the old phone here as my side camera. Then I've got my laptop webcam here for my face shot. And finally, I've got my iPad as a top-down so that you can see my hand on my desk. And everything is being recorded with that microphone there. And then I have my dad helping me out recording on his iPhone just for this shot so I can show you all of the many cameras. Anyway, I'm gonna try a new kind of content for a bit. Let me explain. I love math, okay? I'm a nerd, I'll admit it, I'm proud of it. But it took me a while to realize that because of how much I hate math classes. I apply the stuff that I learn outside of school. I just have trouble learning it in a classroom environment. So this semester in particular, for those of you that don't know, I am struggling through Calc 2 for the third and final time. Like, this is my last retake. If I don't pass this, I don't get a degree. Now, I learn a lot better if I'm able to teach something to someone else. Like, if I can understand it enough to teach someone, and by teaching them, I'm kind of teaching myself too. Anyway, I figured it would be cool to make a video series on this course. Now, a couple of disclaimers with this. I am not legally allowed to publicly distribute course material, homework, lectures, anything like that, so all the problems that you see me do are going to be made up. I'll be paraphrasing things so that I'm not directly quoting lectures. And two, this video series is not intended to be a replacement for a math class. It's just me explaining what I learn as I understand it. This video series is for people that have already taken the class and want to scream at my stupidity in the comments. People that are taking this course right now and want to watch this in parallel so that they can get someone else's perspective and maybe something they didn't think about. Or people that are thinking about taking this course and want to get kind of a preview of what's involved. Maybe get like a head start on the class. Or people that are never going to take the course and just like watching me flail around on camera. So I'm going to assume you've already taken Calc 1 and have general knowledge of what derivatives and integrals are. If you don't, this might not make much sense to you, but anyone and everyone is welcome to watch anyway because it's fun, so let's get to it. Also, I lied. I'm using my main phone as the top down now. It's no longer over there because my iPad sucks. Anyway, so to sum up, a derivative is the slope of a tangent line to a function. So let's say we have our function here, f of x, and we want to find the slope of this line here. This line is tangent to this function, meaning it intersects it at exactly one point. Let's call that point A. So that would be the derivative with respect to x of f of x at x equals A. But what if we want to find the function that gets us that value at any point on this graph? That would be f prime of x, or just the derivative with respect to x of f of x. And that is how we notate this with d dx. Now, I still don't entirely understand this notation, but I do know that this is not just some black box symbol. This is actually a significant part of the equation that we can manipulate algebraically and like move around places, and I didn't know that until my third year taking this course. So now you know, you're welcome. You can move this around. That'll come in handy later. Right now, this is basically a derivative. An integral, on the other hand, is often called an antiderivative because if you were to take, this is the symbol for integral, this weird looking crowbar thing, but if you were to take the integral of some function f of x, dx, make sure to put the dx in there, it's the same as here, this is a notation thing, tells us what variable we're integrating. So if I were to solve this integral and then take the derivative of my result, then I would just get f of x, hence antiderivative. So this is an indefinite integral. It's kind of like what we have here with just finding the function to get the value at any point on the graph. But if we have like a similar graph over here and we want to find the integral within a certain range, this is how integrals work. We want to find the integral from here to here, from a to b, let's say. It's not just a single value, because what an integral is the area under this curve. And the way we notate that is integral from a to b of f of x dx. And that will get you the area of this region. That is a definite integral. So, with that out of the way, let's get to learning some, and I'm out of paper. We're not completely out of paper. Let's get to learning some actual new stuff. So we're gonna start with an integration technique called substitution. Now, before we start, something you need to know. Not all integrals are possible. Your integral must fit into this big table of integrals. There are a lot of things there, but something I learned later on that they should really make clear up front is you can't just integrate any function all willy-nilly like you can with derivatives. You can derive almost anything, but there is an extremely limited set of integrals that you can do, because not all equations are derivatives of something. An integral is an antiderivative, so in order to solve it, there has to be a derivative in the first place. Now, I don't know if that's true in higher levels of math. There might be a way to integrate anything that I just haven't learned yet, but in this course, not all integrals are possible. That's what we're dealing with. Now, that being said, you can manipulate integrals a number of ways to fit into that table. For example, let's consider this integral. Alright, so we're gonna try to solve this. This is ugly. This is very ugly. So what we're gonna do is take this boy and be like, get out of here, nobody likes you. So that we've got the integral of 6x cubed times nothing to the 6 dx. Now you might be like, Davis, you can't just do that. And you're absolutely right. But this is Calc 2 where nothing makes sense. So I totally can. Now don't worry, we don't just get rid of it. We replace it with u, because what we actually did here was we said u equals negative 3x to the 4th plus 3. Now, this isn't legal either. We actually can't do that, because now we've got two variables here. So what we need to do to solve that is we take the derivative of u, we say du equals the derivative of this equation, negative 3 times 4x cubed with our derivative rules here, and constant goes away, dx, or negative 12x cubed dx. And now, what we're gonna do to get rid of this dx here is solve for dx here to figure out what it equals in terms of du. So we say du, divide both sides by negative 12x cubed. This is where some of that algebra stuff came in that I told you can treat these like variables. So du divided by negative 12x cubed equals dx. So now we've got our u, we've got our dx, so we're just gonna plug that in. So this is wrong. We're actually gonna say integral of 6x cubed times u to the 6. And then for our dx, that is actually du over negative 12x cubed. Now, we've still got an x in there, but what do you notice about this equation? This is an x cubed, this is 1 over x cubed. So these are gonna actually cancel out, and that is the key part of substitution. When you choose your u, the derivative of u has to be somewhere else in the equation so that all of your x's cancel out. This takes some practice, but once you do a lot of these problems, you'll get to recognize that. So really, this is integral of, I'm just gonna say 6 over negative 12. The x's cancel out, and then we're left with u to the 6 du. And then I can pull this constant out here. I can also simplify that because that's just 1/2, so I can say negative 1/2 times the integral of u to the 6 du. Hey! That's in the table! And it's super freaking easy too. So to solve that, we say negative 1/2 times 1/7 u to the 7th, following the simple power rule for integration. And now we just need to replace u with what we originally set it to be in terms of x, because that's the answer that we want. And the thing you always need to remember with this, oh my goodness, I always forget. Your u is typically gonna be the inside of something, like here it's the inside of these parentheses. But when you're done with this, you need to remember to apply whatever was on the outside, like this exponent here. This is to the 7th, so you can't just say 1/7 negative 3x to the 4th plus 3. You gotta put to the 7th. Maybe that's obvious and I'm just dumb, but this is 1/2 times 1/7 quantity. For u, we put negative 3x to the 4th plus 3. All of that to the 7th and quantity. And then we just simplify this to be negative 1/14. Now, if you didn't learn this, when you're doing indefinite integrals, this is not done. We're missing a very important part of the equation that if you're taking this into class, you will get marked off for. You remember how I said an integral is an antiderivative? So if we were to derive this, we would just get this again, right? But when you're doing derivatives, what happens to constants? They go away, right? So how do you know that this isn't like tacked on with another constant? In order to solve that, we do a simple thing. We say plus c. That means any constant can be added to this, and when you derive that, it just goes away and you get this. Everyone always forgets this, so to help me out anytime I'm doing calculus, whether it be homework, quiz test, just before I start, I just yell to myself, plus c! Just plus c! Don't forget it. At the end of every problem, even if it's in your head because you have to be quiet, just plus c! When you think you're done, you're about to box your answer, plus c! Alright, I think I've made my point. This is our answer, we're done. That's how you use substitution. Now, we're gonna take this a step further. This was substitution. Now we're gonna work with integration by parts. Parts? Parts! That's right, okay. So, we've established if your integral is not in your table and you can't easily flip stuff around to make it in your table, try a u substitution. If that doesn't work, like if you can't find your x to be your derivative to your u or whatever, then you can try integration by parts. That's our next step. So, the way this works is it stems from the product rule using derivatives. So we already know that the derivative of f of x times g of x times g of x is the same as f prime of x times g of x plus f of x times g prime of x. That's our product rule right there. And remember, f prime of x is just a different way of notating d dx of f of x. It's the same thing, just notation. So what we're gonna do to apply this to integrals, just slap an integral on both sides. Bada bing, bada boom. Oh, and our dx's. Can't forget that. Now this integral has a sum in it, so it can be split right down the middle, like, so now that's two integrals. And then all we gotta do is some algebra, solve for this boy. So that is gonna be the derivative of f of x times g prime of x dx equals f of x times g of x. Because remember, taking the derivative of an integral just gets your original functions, so this is that, and then minus this part, which is integral of f prime of x times g of x dx. Now this is the formula, but those are functions. That's ugly. I want to make them just a variable. So we're just going to do a substitution like we did before, except different. It's similar. But right now we're just replacing the whole function with a variable. That's a thing we can do. So we're going to say f of x is u, g of x is v. So that means that this whole thing is integral of u times dv, because g prime of x is just the derivative of v, since we made that substitution, equals uv minus the integral of v du. That is the integration by parts formula. Commit it to memory. It is extremely important. So this is the formula. You get it? Alright, so when you're actually using this, you want to choose your u and your dv such that it satisfies two things. One, you want the derivative of u, your du, to be easier to work with than your u was. So like reducing a power, getting rid of something. And then you want to choose your dv so that the integral of dv is possible, because that's how you get v. So let me demonstrate. Let's say we have integral 20x e to the 8x dx. This is ugly. This doesn't fit anywhere. Let's try a u substitution. If we say u equals e to the 8x, our du is then gonna be 1/8 e to the 8x dx. I don't really see that anywhere in here. Let's try a different one. If we make u equals 20x, then our du is just 20 dx. And that's a constant, so that works. Let's try it. Du over 20 equals dx. So then we're left with integral of u times e to the 8x du over 20. That simplifies to 1/20th. I'm just gonna go ahead and pull that out. U e to the 8x du. Now that's cool, except there's still an x in there. If that was a constant, then we could just pull that out and we'd be done. But there's no way to get rid of that x. So let's try parts. Parts? Okay, so I'm just gonna write down this formula. Integral of u dv equals uv minus integral of v du. So that's the formula we're working with. We just need to choose values for those variables based on this equation. So the sensible things to make things are either 20x or e to the 8x. Let's try u equals e to the 8x. So then du is 1/8 e to the 8x. Or wait, no, this is derivative, you dingus. 8 e to the 8x dx. So then that leaves our dv to be 20x dx. So then taking the integral of that, I'm just gonna pull out that constant, is 20 integral of x dx, which means our v is 20 integral of x is 1/2 x squared. So that works. Everything is possible, but nothing really got simpler. If we were to plug this in, that would make things just so much more complicated. And that might be the way to go sometimes, but I think the other way might be a little simpler. Let's try that. So that means we're gonna let u equal 20x, which means our du is just going to be 20 dx. That looks better. And then our dv is then e to the 8x dx, which means our v is the integral of that, and that is 1/8 e to the 8x. That looks a little bit nicer to work with. So let's go ahead and plug in all of these values into that formula. So that leaves us with, this is our integral, this is that. So we're just doing this side of the equation. So this equals uv, that's 20x times 1/8 e to the 8x, minus the integral of v du. So that's 1/8 e to the 8x times 20 dx. So these two things are equal. Now let's clean this up a little bit. I'm going to combine the constants. 20 over 8 is 10 over 4 is 5 over 2. X e to the 8x minus, I'm going to pull out the constants and combine them. So that's 5 over 2 times the integral of e to the 8x dx. Whoa! That's an easy integral. That's in our table. What a heckin' coincidence! Now you see why this is so useful. So now we just go 5/2 x e to the 8x minus 5/2 times the integral of this. We're just going to solve that, is 1/8 e to the 8x, and then we can just combine our constants. I'm just gonna erase this and do that because I don't feel like writing another line. So that would be 5/16 e to the 8x, and we're done. That's our answer. That's what this integral is. You see how easy that was?
Did I actually just forget plus c?
Integration by parts is a freaking lifesaver. Let's try another one.
I literally forgot plus c.
Let's say integral of -6x times e to the 6x squared dx. Now that's interesting. We got like nested exponents and everything. So let's see. I want my u to be so that the derivative is simpler and dv so that the integral is possible. Let's do something similar to what we did up here. Make our u equals -6x, du equals -6 dx, And then our dv is e to the 6x squared dx. Now to find the integral of e to the 6x squared, let's see. I don't think that's really in the table. Could we try like a u substitution? No, because the derivative would get us an x and there's no other x in here. Yeah, I'm not sure there's quite a way to solve this. And we already saw with this one that switching them doesn't do much. So what left is there to do? Unless we erase all this, because I intentionally, for your sake, skipped a very important step, and that is to check to see if any other method works. Sure, this isn't in the integration table, but we didn't try a simple u substitution. Now you might think, this is more complicated than that. Wouldn't that just not work? Because there's like another exponent there. Oh, well clearly, integration by parts doesn't work. I just tried it. So let's try a u sub. U equals, I'm gonna go with 6x squared because we can do this. So maybe if we just get rid of the 6x squared and like do that, maybe that'll work. So u equals 6x squared, du equals 2 times 6 is 12x. dx. Solve for dx, we got du over 12x equals dx. Plug that in. Integral of negative 6x times e to the u, because we made that substitution. And then we've got our dx equals du over 12x. And we've still got x's in there. But look, it's the same power. And it's the inverse. We can cancel. Negative 6 over 12 is just negative 1/2. I'm going to go ahead and pull that out. Integral of x is canceled. So we've got e to the u du. Holy crap, that's easy. We've just got 1/2 integral of e to the u is e to the u. Derivative of e to the u is e to the u. E to the u is such a nice thing. Why'd I put another integral there? 1/2 e to the, I'm just gonna sub this back. We've put 6x squared for u. And that is our plus c. Ah! I literally forgot plus c. Ah! There's our answer. Holy crap. Oh, that actually kind of hurt my eye. So we actually didn't need integration by parts for that one. We could do it with a u substitution. Let's do another one that actually needs parts. Parts? How about integral of 5x sine x dx? That's right, we're bringing some trigonometry in this boy. So that's not in our integration table. U sub, I mean, derivative of 5x is just 5, that doesn't really help. Derivative of sine x is cosine x, that doesn't really help. Let's try parts. Parts? U equals, let's try 5x. du is 5 dx. That's simpler, right? dv is sine x dx. v is integral of sine is negative cosine. Gotta be careful with the signs when you're integrating and deriving sine and cosine. Mind the sign of the sine. Because if your sine is sine, then the sign for sine is a sine. uv, that's 5x times minus cosine x minus the integral of v du. That's negative cosine x times 5 dx. I'm gonna clean this up a little bit. Got negative 5x cosine x minus a negative is a positive, so we got plus 5 integral of cosine x dx. Whoa, that's easy peasy. That's just negative 5x cosine x plus 5 times this integral is integral of cosine x is just sine x. So negative 5x cosine x plus 5 sine x. If you wanted, you could factor out this 5. I usually leave it like it is. Plus c. There is your answer. Yeah. So once you pick your u and your dv, you just gotta plug and chug. You'll know within a few seconds if you got it wrong. It's pretty great. Now let's try another one. Let's do integral of e to the x sine 2x. Or wait, hang on, no, that's different. Oh, what do we do here? I know there's a formula for this, but I'm just gonna do a u sub. So this was not our v, our v was negative 1/2. So let's plug and chug. Just gonna combine things here, so that's negative 1/2, a little bit easier to read. So that's actually gonna be a plus. That didn't make things worse, but it didn't really make them better. Let's try it anyway. We're gonna ignore all of these don't matter anymore. Cosine of 2x, wait, no dx. So now, so this is just what we had here. We could just keep going with this and alternate between sine and cosine and just add more to the left-hand side of this. But that would quite literally be insane. I mean, we're just doing the same thing over and over again and expecting a different result. This is the exact same thing as this. We're just going in a circle. But wait, that's exactly what we want. Because remember, this is Calc 2 where nothing makes sense. It is insane. So let's make an equation out of that. We can make an equation out of this. No, don't. All of this madness. I'm gonna to both sides, you know what I'm doing, this madness, but then this integral goes away. Divide by this coefficient, it's a fraction, so we 5/4 times minus a half, x cosine 2x, 5/16. There's no integral on this side. That's straight math. That's the answer to the problem. We just solved our problem with, like, magic. Except it's not magic, it's math. Frickin' algebra. So that is our plus C! Our answer. Oh, the page was off the screen the whole frickin' time. Did I just do that whole thing? Yeah, so I definitely just realized the bottom of my page wasn't visible that whole last part of the clip. So hopefully my editing skills are on par. So, I already used that side. Let's try another one. How about something super simple? Integral of natural log of x dx. Now, it's actually so simple that there's really not a lot you can do with it. I mean, is it in the table? Is it just 1 over x? Nope, that's the derivative of natural log x. Don't get that confused. So you can't really substitute anything. Let's just try parts, because it might seem like there's only one part to this, just natural log x, but you're forgetting the dx. Because there's actually a 1 right there that we just don't write, because what's the point of writing 1 times anything? But anyway, we're gonna write u equals natural log x, and then dv equals dx. Whoa, you can do that? Yeah. Alright, so then our du is 1 over x dx, because the derivative of natural log is actually 1 over x. And then our v is just x. Crazy, right? Okay, so let's plug this in. uv, x natural log x, minus integral of v du. So that's x times 1 over x dx. Well, that's interesting, because this just cancels out. So we're left with x natural log x minus integral of 1 dx is just x. So that we're done? Actually, I need to check my notes, because that went even quicker than I remember. Yeah, I think that's it. So that is our plus C! Is our integral of natural log x. So let that be a sub-lesson to integration by parts, even if it looks like there's only one part. Nah, fam, there's a dx in there, and you can just make dv equals dx and then v equals x. Easy freaking peasy. Now, let's try... Oh, I bet that's gonna bother a lot of you. Integral of secant to the 5th x dx. Okay, so turns out that's a really freaking hard integral. I just showed you the steps on photomath. I'm not even gonna solve it myself. They did it in the lecture, and I never want to have to do that ever in my life. Don't be deceived. This looks so friendly, but it's really, 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 really not. I'm sorry, this is supposed to be a preview of the fun that Calculus 2 is. Oh, what's next? Wanting death? Yeah, that sounds about right. Actually, I think that's about all I had for you anyway. So yeah, we reviewed what derivatives and integrals are. We did u substitution, we did integration by parts with a few different methods, and I made those of you who need to take this class fear for your life. Sounds like a day to me. For those of you who are returning to my channel, I just want to say that I will continue with all of my projects and music and everything. Just in these next few months, I really, really, really need to focus on school, because like I said, this is my last shot at this class. So hopefully I can keep up with these videos. Hopefully it'll help me. Hopefully it'll help you. I really hope you found it helpful. If you did like this video, please let me know using the like button. Also, definitely share this video with your friends that might also be struggling with Calc 2. And if you're not already subscribed, I'd encourage you to do so. It really helps me out, and you get to see all of my many adventures yet to come. If you want to support me further and help grow this channel, you can visit my Patreon page, link is in the description. Either way, thank you so much for watching, and until next time, make something, sing something, virtually hug someone, and I will catch you in the next video. Good day. Oh shoot, my fellow scholars. Oh, is my iPad not? Oh, for frick's sake. Oh, my laptop wasn't either. Check some things. This wasn't either. What the fudge muffin? My phone, the only reliable camera I own?